In today's lecture, we shall see how we can develop some numerical integration methods. So, we work out the details for error in trapezoidal rule. So, what is the error in interpolation? F of x minus p1 of x, and we have already obtained the expression for error in interpolation at any x which belongs to the interval x0 to x1. So, what is the error in the interpolation? It is f of x minus p1 of x, and that is equal to the second derivative evaluated at psi divided by 2 factorial multiplied by x minus x0 into x minus x1 for psi lying between x0 and x1. And therefore, error in this evaluation of the definite integral will be obtained by integrating the error in interpolation between x0 and x1. So, p1 of x dx will be equal to integral x0 to x1 f double dashed of psi by 2 factorial into x minus x0 into x minus x1 into dx. So, by using mean value theorem for integral calculus, we have f double dashed at some eta by 2 factorial into integral x0 to x1 x minus x0 into x minus x1 into dx. So, eta is now in x0 to x1. So, this will give you f double dashed at eta by factorial 2 into, let us evaluate this. So, x0 to x1 of x minus x0 into x minus, I use the fact that x1 is x0 plus h. So, that gives you f double prime eta by 2 into x minus x0 the whole square minus h into x minus x0, and that must be integrated with respect to x. So, by 2 into x minus x0 the whole cubed by 3 minus h into x minus x0 the whole square by 2 between the limits x0 and x0 plus h. So, this gives f double prime eta by 2 into at the upper limit x0 plus h. This will give you x0 plus h minus x0. So, h cubed by 3, and at the lower limit this will vanish. And the next term minus h into at the upper limit x0 plus h, this will give you h square by 2, and at the lower limit this will vanish. So, this gives you f double prime eta by 2 into h cube into 1 by 3 minus 1 by 2. So, that will give you minus h cubed by 12 into f double dashed at eta, eta lying between x0 and x1. So, error in trapezoidal rule is this, where h is the step size, namely the width of the interval. So, you now can write down the trapezoidal rule as, if you want integral x0 to x1 f of x dx, then it is h by 2 into f at x0 plus f at x1 plus the error, namely minus h cubed by 12 into the second derivative at eta. So, if I ask you to evaluate integral say 0 to 1 dx by 1 plus x by trapezoidal rule, then it is simply h is 1 because b minus a into f at 0 plus f at 1, and by doing this you have made an error of h is 1. So, 1 by 12 into f double prime at eta, where f of x is 1 by 1 plus x. So, this essentially will give you half of f of 0, f of x is 1 by 1 plus x. So, f of 0 is 1 plus f of 1 is half. So, the result is 3 by 4. Then the error committed is minus, the error committed is minus f double prime eta divided by 12. So, if you want the bound on the error, then it will be the absolute value of f double prime eta by 12. Knowing f of x, which is 1 by 1 plus x, you can compute the second derivative. So, the second derivative will be f of x is 1 by 1 plus x, f dashed of x will be minus 1 by 1 plus x the whole square, and f double dashed of x will be 2 by 1 plus x the whole cubed. So, if I want the bound on this error, then this will be minus f double prime eta by 12, and so I observe that this will be less than or equal to the maximum of f double prime of eta by 12, and so for maximum I take this eta belonging to the interval 0 to 1. Having computed the second derivative, I observe that the maximum will occur at x is equal to 0, and therefore it is 2, and so the result is 2 by 12, and so 1 by 6. So, the error is always bounded by 1 by 6 in this approximation of the interval which is given by this. So, this method was obtained by approximating f of x by a linear polynomial. So, we move ahead to see what happens if we approximate f of x by a second degree polynomial, namely a quadratic interpolation polynomial. The resulting method that we get is called Simpson's rule. So, we shall derive now Simpson's rule. The method is obtained by approximating the function f of x, which has to be evaluated in this interval by a polynomial of degree 2. So, I take my n to be 2 because I am interested in deriving Newton-Cotes method. So, I would like to get a method which is of the form sigma k is equal to 0 to 2 Lk of x into f of xk. So, this will be L naught of x into f of x naught plus L1 of x into f of x1 plus L2 of x into f of x2. So, I have to integrate this with respect to x. So, integral of this with respect to x. So, which will give me sigma f of xk into integral a to b Lk of x dx for k is equal to 0 to 2. So, this will be k equal to 0 to 2 f of xk. I shall call this integral Lk of x dx to be ak. So, I am interested in getting the constants a naught, a1 and a2 in this formula, where a naught will be equal to integral a to b L naught of x dx. A1 is integral a to b L1 of x dx, and A2 is integral a to b L2 of x dx. So, I require 3 points x0, x1, x2, and we are deriving Newton-Cotes method. So, the points must be equally spaced. So, I shall take the points x0, x1 and x2 to be such that xi is x0 plus ih for I is equal to 0, 1, 2. So, my x1 is nothing but x0 plus x2 by 2, the midpoint of the interval. So, I evaluate the ordinates at these points. So, I have the information about the ordinates because I know what f of x is. If I evaluate a0, a1, a2, then I will have the formula where f of x is approximated by a quadratic interpolation polynomial. So, we write down what these Li of x are. So, L naught of x is equal to x minus x1 into x minus x2 by x naught minus x1 into x naught minus x2. L1 of x will be x minus x naught into x minus x2 by x1 minus x naught into x1 minus x2, and L2 of x is x minus x naught into x minus x1 by x2 minus x naught into x2 minus x1. So, I have integral a to b. What is my a? A is x naught and b is x2, and the midpoint is a plus b by 2. So, I require integral x naught to x naught plus 2h of L naught of x dx. So, I can rewrite this as x minus x naught minus h into x minus x naught minus 2h by x naught minus x1 is minus h, x naught minus x2 is minus 2h. So, I have x minus x naught the whole square, then minus 3h into x minus x naught plus 2h square divided by 2h square. So, this will give me integral x naught to x naught plus 2h 1 by 2h square into x minus x naught the whole square minus 3h into x minus x naught plus 2h square integrated with respect to x. So, you have h cubed by 2h square into 8 by 3 minus 6 plus 4. So, h by 2 into 8 by 3 minus 2. So, h by 2 into 2 by 3. So, you end up with h by 3, that is integral L naught of x dx. So, similarly, we must evaluate integral L1 of x dx and L2 of x dx. And what is it that we have got? We have obtained the value of the constant a naught, which is integral L naught of x dx. So, let us now compute a1. So, let us simplify L1 of x. So, x is x minus x naught into x minus x naught minus 2h by x1 minus x naught is h, x1 minus x2 is minus h. So, this gives you x minus x naught the whole square minus 2h into x minus x naught by minus h square. So, integral x naught to x naught plus 2h of L1 of x dx will be integral x naught to x naught plus 2h x minus x naught the whole square minus 2h into x minus x naught by minus h square into dx. So, minus 1 by h square into, let us evaluate, x minus x naught the whole cube by 3 minus 2h into x minus x naught the whole square by 2 between x naught and x naught plus 2h. So, that gives you minus 1 by h square. At the upper limit, it is 2h the whole cube by 3 minus 2h into 2h the whole square by 2. That gives you minus h into minus 4 by 3, and so the coefficient, the constant a1 is 4h by 3. Similarly, we evaluate integral L2 of x dx. So, let us simplify L2 of x, which is x minus x naught into x minus x1. So, x naught minus h by x2 minus h naught, which is 2h, x2 minus h1 is h. So, 2h square into x minus x naught the whole square minus h into x minus x naught. So, integral x naught to x2 L2 of x dx will be 1 by 2 h square integral x naught to x naught plus 2 h of x minus x naught the whole square minus h into x minus x naught integrated with respect to x. So, this will give you 1 by 2 h square into first term integrated will give you x minus x naught the whole cube by 3 minus h into x minus x naught the whole square by 2 between x naught and x naught plus 2h. So, apply the limits of integration. So, 1 by 2 h square at x naught, this will give you 2h the whole cubed. So, 8h cubed by 3. This will give you x minus x naught will be x naught plus 2h minus x naught. So, 2h the whole square divided by 2 into h. So, this will be h cubed. At the lower limit, they vanish. So, this gives you h cubed by 2h square. So, h by 2 into 8 by 3 minus 2. So, h by 2 into 2 by 3, and the coefficient, the constant is h by 3. So, what we have evaluated is a2. So, we have the constants a0, a1 and a2 determined. So, we write down the method which says integral x0 to x0 plus 2h f of x dx is a0, which is h by 3 into f of x0 plus a1, which is 4h by 3 into f of x1 plus a2, which is h by 3 into f of x2. And so, this gives you h by 3 into f of x0 plus 4 f of x1 plus f of x2. So, let us see what this formula tells us. So, if we want to evaluate integral f of x dx between x0 to x0 plus 2h, then it is h by 3 times f of x0 plus 4 times f of x1 plus f of x2. So, namely, if x0, x1, x2 are equally spaced such that the step size, the distance between any 2 points is h, then the formula tells this integral has a value which is approximate and is given by 1/3 of this h multiplied by the sum of the end ordinates, namely f of x0 plus f of x2 plus 4 times the ordinate at x1. So, 4 f of x1. It is easy to remember. right, applying Simpson's rule is equivalent to getting the sum of the end ordinate values plus 4 times the intermediate ordinate, namely the ordinate at the midpoint of the two end points, and multiplying it by h by 3. What does it actually mean? Let us see geometrically. So, we have in the xy plane a curve y is equal to f of x, and we are asked to integrate between x naught and x naught plus 2h. Namely, we are asked to get the value of, we are asked to find the area bounded by y is equal to f of x, the ordinate at x naught and x2, and the x axis between x naught and x2. So, what did we do? We approximated this function f of x by a parabola passing through the points x naught, x1 and x2. So, we have a quadratic interpolation polynomial, namely a parabola passing through these 3 points, so that this parabola approximates this curve, which is y is equal to f of x. All right, and we have evaluated the area, which is now this bounded by the parabola, which is this, the axis at that point. Clear? Our parabola is here. This is our parabola passing through the 3 points, right. So, the shaded region is the area that we have computed. So, in doing that, we have committed an error, namely this part of the area has been omitted and this part of the area has been included. And so, some amount of error has incurred in obtaining this integration method, namely in Simpson's rule. So, our goal now is to see how much of error is incurred in obtaining Simpson's rule, and as before, we can get this error by integrating the corresponding expression for error in interpolation. So, we observe that we have derived Newton-Cotes formulas by approximating a function in an interval by a linear polynomial, and we obtained trapezoidal rule, and by a quadratic interpolation polynomial, and we obtained Simpson's rule. And these rules are valid for the case when the nodes are equally spaced, and geometrically they represent the corresponding areas bounded by a trapezium in the case of trapezoidal rule, and the area bounded by a parabola passing through the 3 points x naught f of x naught, x1 f of x1, x2 f of x2, and the ordinates at the end points and the segment along the x axis between the end points. That is the geometric way of looking at this Newton-Cotes formulas when n is equal to 1 and n is equal to 2. So, one thing that remains to be done is computation of the error in Simpson's rule method for evaluating an integral.